Kazakhstan is a country located in the heart of Eurasia, appeared on the geopolitical map only in 1991. It is bounded on the northwest and north by Russia, on the east by China, and on the south by Kyrgyzstan, Uzbekistan, the Aral Sea and Turkmenistan. The Caspian Sea bounds Kazakhstan to the southwest. Kazakhstan is the largest country in Central Asia and the ninth largest in the world. For centuries, the Great Kazakh Steppe accepted caravans of the Silk Road in oases of its cities and settlements. It was historically closely tied to the Silk Road trade routes, acting as a crossroads for the movement of people, goods and ideas between Europe and Asia. The capital of Kazakhstan and it's the largest business center is Nur-Sultan. The third megapolis of the country, Shymkent, is as a city in the south of Kazakhstan with an 800 years history, founded in the 12th century. Nowadays, Shymkent is a city of national significance, one of the largest industrial, commercial and cultural centers of the country, the third largest by population of more than 1 million people. One of the large multidisciplinary education institutions of Kazakhstan with a deep history is located here. It is Awezov University. That is, here students and undergraduates acquire practical working skills. In other words, this is a mini copy of a large production and dairy plant. Within the framework of the program of scholarship, academic mobility and double degree education, the university cooperates with more than 170 foreign universities. 150 students a year study for the academic mobility at leading universities in the world. The digitalization process has affected all spheres of society, including education. At Awezov University, innovations are intensively introduced into the education system, and 3D, VR, STEM technologies are widely used. The IT Center provides consulting to teachers of schools in Shymkent on robotics, provides material resources to students in the Laboratory of Robotics and Mechatronics at the Laboratory of Mathematical and 3D Modeling, and provides material resources of the IT Center to students and teachers of the Awezov University. In Student Design Bureau, students and teachers prepare scientific projects for participation in regional, national and international competitions. Students of clubs and Student Design Bureau develop robotic systems for participation in competitions and competitions in robotics. The material and technical base of the university consists of 10 educational buildings of a modern standard, 6 student dormitories and 2 sports complexes. For the comprehensive development of students, more than 30 public, political and cultural organizations function. Awezov University, that has united history and modernity, today prepares more than 27,000 students and invites to take your best.
Здравствуйте, уважаемые участники.
I greet you all, my distinguished participants, and Spergel Jandos. I'm a moderator. I'm a PhD assistant professor from South Kazakhstan University, called after Awezov. And in today's meeting, we have a very important speaker, and he will make a lecture for our Awezov University, emeritus professor of Princeton University, and who got the Nobel Prize for a breakthrough discovery in 2018 in physics. And today we are going to talk about machine learning and cosmology. And briefly, some words about this, using microwave background, using the probe and using the cosmology telescope, they've been able to measure the form and the content of the universe. And we are grateful for your participation, Professor. And the floor is yours, Professor. Please.
So thank you. Let me bring up my slides. So what I want to talk about today is in some ways a dream. I want to begin by telling you what we have done in the past 20 years in the field to learn more about how the universe began, to get a glimpse of its early moments, and then want to look forward to the data that we will be getting in the coming decade and talk about some of the techniques that we are trying to develop using some of the tools of machine learning that I hope will enable us to discover even more about the properties of the early universe and to use that to gain new insights into the basic physics that describes our universe. This lovely scene I'm showing here comes from the mountains of Chile. Chile is one of the driest places in the world, and as such represents a fabulous site for observing the microwave background. What you see here is the plains above the Atacama. In the foreground of the image, you see the Atacama Cosmology Telescope, the Simons Array telescopes a little bit further, and far out in the distance, in the plain below, you see the ALMA array, an array of radio telescopes that have given us important insights, not only into cosmology, but into areas like planet formation. So I want to begin by first giving you a review of cosmology, to give you an overview of the field, then look at how we observe the cosmic microwave background, the leftover heat from the Big Bang, and how those fluctuations have given us significant insight into the early universe. Then turn to how those fluctuations grow to form galaxies, look at the process briefly of galaxy formation and the upcoming observations, the upcoming data explosion, and then try to describe some of the techniques that we are working on developing to be able to infer more information from the data that will be coming from these observations in the coming decade. So let me begin by talking about cosmology. The key idea for me when start with cosmology is that light travels at a finite speed. So when we look out in space, we look back in time. It takes light 8 minutes to travel from the sun to us. So we see the sun not as it is now, but as it was 8 minutes ago. The sun doesn't change that much in 8 minutes, so it's not such a big effect. But the further out we go, the more dramatic this effect is. When we look at the typical star in the night sky, it might be 50 or 100 light years away. That means we see the star as it was 15 years ago. We look out at a nearby galaxy, like the Andromeda galaxy, we're seeing it as it was roughly 1 million years ago. An observer sitting in a planet in the Andromeda galaxy would see us as we were 1 million years ago, because it takes light 1 million years to travel. And the further out we go in space, the further back we go in time. This is what makes the cosmic microwave background observation so interesting. The pattern of fluctuations that we see in the cosmic microwave background, and this globe represents some of the observations we've taken, are fluctuations that have been traveling to us for 13.8 billion years. And when we observe the cosmic microwave background, we are seeing physical conditions, as these fluctuations represent variations in temperature and density and fluctuations generated by the velocity of the electrons. We're seeing physical conditions 380,000 years after the Big Bang, 13.8 billion years ago. And our story begins with these observations of the microwave background. The first observations of the fluctuations were made by the COBE satellite, led by John Mather, George Smoot, which late gave rise to their Nobel Prize, and it mapped the fluctuations across the largest sky. The team that I was part of, and my own role was to lead the theory and interpretation of these results, launched the Wilkinson Microwave Anisotropy Probe, a NASA-built mission that launched in 2001 and operated for 9 years, mapping the fluctuations at much higher resolution. You can see the same patch of the sky observed roughly a decade later at even higher resolution. And we were able to make this map of the sky and characterize the fluctuations. This data was made public now almost 20 years ago. A decade ago, the European Space Agency launched the Planck satellite that has measured the fluctuations at even higher resolution. You can see even more details emerge, and with those more details, higher quality of information, more insights into the properties of the universe. And this pattern of ever improving observations rests on first building bigger dishes, but primarily in developing new technologies that enable us to probe the fluctuations with increasing sensitivity. And this gives you a picture of the map of the whole sky from the Planck satellite, showing the very fine details that they've been able to measure. These observations show variations in temperature and position at millions of positions of the sky. More recently, and I showed you some pictures from the Atacama, we have been taking even higher resolution images from the Atacama Desert, shown here at the border between Chile, right near the border between Chile, Bolivia, and Argentina, at a height of about 5,700 meters. So a very high, dry place to observe. And you can see how these represent an improvement. Here's the Planck data. Here's the ACT data over the even very high resolution Planck data. And you can see as we go to this even higher resolution, we see these bright red spots, which are emission from quasars. We see these blue dots, which are actually clusters of galaxies seen as shadows against the microwave sky. an effect predicted by the Rashid Sunyaev in working with his advisor, Yakov Zoldovich. Sunyaev and Zoldovich were among the people who developed much of the theoretical framework that we use to interpret the microwave background observations. Zoldovich passed away many years ago. Rashid Sunyaev remains a very active researcher. We believe now in his late 70s. Now, how do we analyze this data? What we do is we take the temperature across the microwave sky and we expand this out in spherical harmonics. For those of you who have done Fourier analyses, you can think of spherical harmonics as Fourier modes on the sky. And since the sky is observed to be isotropic, all of the information in the spherical harmonics is contained in the angular power spectrum, the C sub Ls. So we can take those millions of points on the sky and reduce all the information in the observations until the 2-point function embedded, contained with these C sub Ls. And what we do for our data analysis is we fit the data with a theoretical model with a handful of parameters here characterized by the letter P. In practice for us, those parameters in our simplest models are simply 6 numbers: the age of the universe, the density of atoms, the density of matter, how lumpy the universe is, how that lumpiness varies with scale, and a parameter that characterizes when the first stars formed, because the ionized gas between us and the surface of last scatter affect the fluctuations. So what these equations represent is vastly compressing the data, starting with millions of observations, and in the end fitting this with 6 numbers with a Gaussian likelihood function. And this shows where we think we will be with the data, just giving you a sense of where things are going. One of the things we are building right now in Chile is the Simons Observatory, an international collaboration, significantly funded by the share of the funding coming from the Simons Foundation, an organization that I'm actually now president of. I started working on this project before joining here, and now find myself in charge of the organization that's responsible for funding and helping to build this. But this shows how our measurements will continue to improve, eventually being 5 times the resolution, 10 times the sensitivity of the Planck experiment. This shows where we are today with the data. The blue points representing the Planck measurements, the red points, the ACK measurements that I've shown, the yellow points, measurements taken from the South Pole by the South Pole telescope, the green, the polar bear experiment, another experiment in Chile, and BICEP and Keck are an experiment in the South Pole. And what's plotted here is the amplitude of that angular power spectrum, how that amplitude varies with scale. The points are the data. The line is our theoretical model with our 6 basic parameters. And I think you can see from this plot first, I think the thing you should see from this plot is the tremendous success of the observations. After all, we're looking at 4 or 5 different experiments here, measuring fluctuations in temperature, TT, in polarization modes, in the E's and the B's, their cross correlations. We're seeing millions of measurements across the sky, and you can see in terms of their measurements of the statistical fluctuations, the remarkable agreement between different experiments using different telescopes, different types of detectors, measuring fluctuations at the millionth of a degree level. The units you see are microkelvin or millionths of a degree. measurements of fluctuations in the microwave sky. We are making these incredibly accurate measurements of conditions in the very early universe. And the curves show our theoretical models. And this is a great triumph, I would say, also of theory. You can look at the models that people like Jim Peebles, who won the Nobel Prize for this work back in 2019, did work that Sunyaev and Zoldovich also did, and all those components come together to, on the theory side, and the theory, these curves are a beautiful fit to the data. My own work has involved developing a number of the techniques in the data analysis that has let us compare these two and make these precision inferences on the basic properties of the universe. So this data lets us determine things like the age of the universe, 13.8 billion years, with an accuracy of only 100, uncertainty of only 100 million years. So we've now very accurately determined many of the basic parameters of the universe. This leaves us in a very interesting place in cosmology, where in some ways we have been remarkably successful. This plot is a great triumph, where we have a simple theory with only a handful of numbers that fit a host of observations, and as I will show soon, give us the information that tells us what are the seeds that form galaxies. The challenge is this model, while simple, is very strange. It implies that atoms, the stuff that makes up us, makes up only about 5% of the universe. The next 25% is in the form of what we call dark matter. Particles that interact only through gravity and have very weak interactions, if any, with ordinary matter. Which means we don't know what makes up most of the stuff of our galaxy. Something that could be quite important for our future understanding, but right at the moment is just a missing piece of our knowledge. The next 70% is made up of what we call dark energy. Energy associated with empty space. Empty space itself seems to affect the shape of space-time. And putting this all together, we don't know what makes up 95% of the universe. For me, this is enormous motivation for the rest of this talk and much of what we are doing in cosmology. We'd like to figure out what's out there. And I think for students who are listening to this, thinking about future research directions, the fact that we don't know what makes up 95% of the universe means there's an enormous amount left to discover. Sometimes I think particularly early in one's studies, you get a sense that there's so much that others have already discovered, and you don't see where your role is to contribute to fundamental science. But I think this points to our enormous ignorance and the enormous work that lies ahead for your generation in understanding the basic properties of the universe. Now, when we do these analyses, what we see is that the fluctuations we see from the early universe are described by what we call Gaussian initial conditions. This is about as simple as the universe could be. When we say fluctuations are Gaussian, what that means is the fluctuations are described entirely by a two-point function, and the distribution of fluctuations. So you see plotted here the number of hot or cold spots normalized by the variance seen in this map of the sky when we smooth it first on the 1 degree scale, the half degree scale, and the quarter degree scale. Oops. And these observations show that the fluctuations seem to be on these scales completely Gaussian. the universe appears to start out in many ways as smooth as it can be. And when we show this power spectrum, we start with the idea that the fluctuations have these very simple properties, an idea supported by observations. These fluctuations then continue to evolve gravitationally and grow to form the galaxies we see. We can also trace the same large-scale structure with models of galaxy formation. And here's a recent paper by Phil Cox and Ivanov, where they have measured here not only the statistical two-point properties of the fluctuations, but some of the non-Gaussian features. And here, these are observations not of the universe at redshift of 1,000, which we're looking at the microwave background 13.8 billion years ago, but the universe looking out to roughly 2 billion years ago and 5 billion years ago, where again, you're seeing, and we won't go into the details here, but just give you a sense of the exquisite match between theory and observation, not only in the microwave background, but in our observations of large-scale structure. And this rests on our basic theory that gravity explains how structure grows and evolves. And this shows a numerical simulation showing how the smooth Gaussian initial conditions can evolve to make the galaxies we see today. And here's another way of thinking about this picture. This shows more how observers would look at this. This is looking at things in terms of time since the Big Bang. Here we are at the present. We look out in space back in time through the large-scale distribution of galaxies. Here's the large-scale distribution of quasars. Here's out to the microwave background. So we observe looking out from the present to the past. I guess I'd like to think of that, that's how the observers see the universe. As theorists, we start with the past, with this microwave background fluctuations, evolve them forward to form the galaxies we see. And this evolution, we start with those fluctuations we see in the microwave background. We can use analytical methods to describe how the fluctuations evolve on the initial larger linear scales. As the fluctuations become nonlinear, we use the kind of numerical simulations that we see here to model on the computer those nonlinear evolutions, that growth of what we like to call the cosmic web. As things become nonlinear, the dark matter and the atoms collapse to form what we call galaxy halos. Those are sites of galaxy formation. That's when things get complex. We have to start including the rich astrophysics of cooling and star formation and massive winds coming out of supermassive black holes. And our simulations, which I'll talk a little bit about, need to include all those things. And then when we look at the large-scale distribution of galaxies, this is the cosmic web. These are observations here of 63,000 galaxies. What we now need to do is compare these observations to the results of these kinds of simulations and match them up and compare them. One of the challenges in doing this, as you can see looking at this picture, nonlinear evolution, and here's the observations, has led to these complex nonlinear structures. So the simple kind of linear Gaussian analysis that we were able to do in the microwave background will not fully capture everything going on the large-scale distribution of galaxies. And one can think of this as our goal is we want to measure the basic parameters of the universe, the density of matter, the density of atoms, the expansion rate of the universe, how the lumpiness varies with scale, what the lumpiness is, and properties of the universe, the mass of neutrinos, the properties of dark energy, the presence of new particles from the large-scale structure data, and address these fundamental questions. What is the nature of dark energy? What are the properties of the elusive neutrino? how fast is the universe expanding? And that also, of course, is telling us about the universe's future. Will the universe continue to accelerate? Will that acceleration get faster and faster? What are the properties of the universe's initial conditions? And the approach people have used up to now is the same approach we used on the microwave background. This standard two-point analysis where you describe everything by how pairs of galaxies cluster. Yet we know there's more information than this power spectrum. There's more data, more things we can learn, and we want to come up with better summary statistics, better ways of extracting information from the large-scale structure. So now I will turn in the rest of my talk from what we have done to what we're hoping to do in the coming decade, and how we hope to develop new techniques that let us move from our observations to our theory. And this is motivated by this data explosion. On the ground, we have telescopes like the Dark Energy Survey, which is measuring as many galaxies in a week as that big galaxy survey I showed measured in a year, operating right now. The Rubin telescope should see first light towards the end of this year. Down in Chile, it will map the large-scale distribution of galaxies and galaxy lensing across the sky. The European Space Agency will be launching the Euclid telescope and in 2023, and NASA the Roman telescope in 25. I think all these years you may have to actually add a year or two with COVID delays, supply chain delays, everything's a little later, that may be 23, 24, and 26, but all these things are coming soon. Right now in orbit, the German-Russian mission, eROSITA, is mapping the whole sky in X-rays, getting its large-scale distribution. And in Chile, we will have a much improved microwave background experiment with the Simons Observatory. So we'll have an enormous amount of new data in the next 5 years. And 10 years from now, these surveys will be nearly complete. And I don't think we have all the tools we need to extract all this data. And we'd like to pull out more information, and we'd like to see that, see what we can learn there. And one way we've been studying how much information is there is by running very large numerical simulations to try to extract information from there. And this is work led by my colleague, Francesco de la Escuela Navarro. What we've done here at the Flatiron Institute, where I'm now spending most of my time, is we have launched a set of 43,000 N-body simulations. These are these gravitational simulations, looking at very different cosmologies, looking at more than 50 trillion particles over a volume that's larger than the entire observable universe, identifying billions of halos. This has taken 35 million CPU hours and generated over a petabyte of data. All this data, by the way, is publicly available. There's information at it at Francesco's GitHub address. So anyone who would like to work with this data and extract something new from it, one of the things we're trying to do is very much operate in the mode of open science and make the data and the ability for others to work with this and test this available and accessible. And we've been working and doing this with a very large team of people located here in the US, in Europe, now some folks in Japan, working together on the analyses of this data. We've been trying to measure the information content here, looking at how much we can extract by applying not only the techniques you see in red, which represent the standard techniques, but adding new techniques, looking at the halos, looking at the voids, combining them all. You can see we can obtain much smaller error ellipses much more accurate determinations of things like the properties of the neutrino and the dark matter, the amplitude of fluctuations. These are the numbers we're measuring. So you can see by combining techniques, we can learn much more. And here's another way of looking at some of these parameters to look at these things. And we've been working on different ways of extracting this information using a number of different statistics. But flashing lots of plots, the takeaway I want from you to have from this is as we add, there is much more information in these observations that we're coming than we're extracting with our current techniques. And this motivates the development of new statistical methods. The challenge is the physics is complex. If we want to model galaxy formation, we need to not only include the physics of dark matter, but include how the gas responds, how explosions drive what happens. And you can see there's a rich amount of information. This is from one of the gas simulations, looking at the large-scale distribution of the distribution of stars, of gas. This simulation shows how explosions from supernova and active galactic nuclei are driving winds into gas, producing fluctuations in pressure, driving material out, forming heavy elements. We can simulate all this with some uncertainty. We try to capture the physics the best we can, but we know when we look at observations of galaxies, that when we get to those scales, which is what our observations are now probing, these observations are reflecting the very rich history you're seeing here. We're watching here galaxies in formation and merging. When we observe a galaxy, what we see reflects not just the total amount of matter, but also some of the galactic history. And we need to find ways to think about that and model that better if we want to infer the full information from the observations. And our goal is to try to marginalize over these effects of winds as we go on. In the final part of my talk, I want to describe some of the things that we're doing. This represents, I would say, our dream. We don't know whether this will work yet. Our hope is we can use machine learning as a way to accelerate our simulations, also as a way to help us marginalize over the uncertainties in the effects of these winds and so on to extract what's going on. And the idea here is to develop a number of different techniques, first to accelerate the calculation, and then to learn how to marginalize over this. And this is work led here at the Flatiron Institute by Shirley Ho, working together with Francesco Villasquela-Navarro and others at our program. And first, let me tell you about work that we've done in the past 3 years here to speed up the calculations. The idea here is we start with our analytical approaches, building on work done by Zoldovich and his group in Moscow back in the 60s and 70s to make analytical calculations. We then take our numerical simulations, look at the difference between analytical calculations and the numerical simulations, teach our neural net to take the analytical simulations, and this uses a conformal neural net to UNet to do this, and improve the predictions. And you can see how well this can do. This shows our errors in predicting the positions. Oops. First, comparing on the left our neural net predictions. The right, the best analytical models we have. You can see the best analytical models have large regions where the predictions of particle positions can be off by 5 megaparsecs. That's pretty big. That's 15 million light years. While our neural net much more accurately represents what goes on. We can see this both in the large-scale distribution of particles or when we look at this numerically. And the beauty of using this machine learning technique is instead of running those n-body simulations I showed earlier and described these massive simulations we did, we can now train the neural net and use it to do things to create more realizations of what happens. And with the neural net, we can now do the calculations about 60 million times faster. That's an enormous speed up and gives us now the numerical tools that we hope will let us do the kinds of analyses that we could not have imagined without these numerical tools. And we're hoping to use this to launch a program where we can actually go back to the initial conditions of the universe, simulate what the dark matter does, simulate the large-scale distribution of galaxies and gas, and compare this to observations. And rather than relying on computer codes that take millions of CPU hours to go from initial conditions to the large-scale distribution of galaxies, we can use our neural net to do this in a million or perhaps even 100 million times faster. And then we can run this loop many, many times, improving our estimate of the initial conditions so that we can recover what's going on and learn more from the observations. For those of you who want a formal equation, you can think of this as asking what is the likelihood of the microwave background observations, the large-scale structure observations, given our initial conditions, the parameters that describe our astrophysics, the uncertainties in our observation, and just marginalizing over all these uncertainties. And we've launched, doing this calculation is challenging. We're trying to model the whole visible universe with a resolution of a few megaparsecs. It's effectively trying to do a calculation where we're solving for over 1 billion variables, along the way marginalizing over our uncertainties and projecting the observations in a way in which we can compare directly to this incoming data from these big surveys. The next step we've taken in this program is a set of simulations also which we're making available called the CAMEL simulations. These include not only the effects of gravity, but the hydrodynamics which I showed of galaxy formation and star formation. And we're using multiple different numerical codes to understand what depends on the details of the simulations, what depends on our modeling of astrophysics. We have very large volumes, multiple simulations, and we've designed the data sets and made them available in ways in which others can use them for machine learning applications. And the goals here are really to provide predictions for comparing these simulations directly to the large-scale observations and develop over the next several years the tools we need so that we are ready when these new observations come, training the networks to be able to connect the simulations to the observations. And along the way, we also hope to better understand how the physics of galaxy formation depends on the underlying subgrid physics. And I think of this as a testing ground for a broader program in numerical physics of comparing large-scale structure, of incorporating subgrid physics into models. Here's showing you, see if I can get this to run. Here we go. 2 sets of simulations with the same initial conditions and different codes. You can see the 2 simulations agree in some ways. Some of these images of the distribution, say, of dark matter look quite similar, but one of the codes treats winds from active supermassive black holes differently. It produces bigger explosions, the one on the right. The SIMBA simulation explosions are bigger, it dries more gas out. And by comparing these kinds of simulations, we get a better idea of which approach represents better the underlying physics of the universe and also which of the observations are most robust to the details of these observations. So this is very much a work in progress, going to higher resolution, developing techniques of likelihood-free inference to compare to data. It's something where we've engaged a large group of people across the world in this project and growing. I'm going to skip some of these recent results and turn to the conclusions and, ask the questions that we're thinking about right now. We've convinced ourselves that this new data is going to demand new techniques, and we can learn more about the fundamental properties of the universe from applying these new techniques to the upcoming cosmological information. There's information beyond the 2-point statistics, the kind of approaches that I used in the 10 to 20 years ago to these kinds of analyses of the microwave sky. We'll need to move beyond them to get the most out of large-scale structure. I'm convinced that machine learning, which is having powerful applications in a wide range of fields, will also turn out to be a powerful tool in this area. I think one of the advantages, and this is really another completely different lecture, which I've given at other times, you can turn this around and say, when I apply machine learning techniques to physical problems like this, what does this tell us about machine learning? Something that I think will be useful as we use to apply it to a wider range of problems. I want to, at this point, come to a close and thank you for your attention. I know that it's challenging often to hear these talks on Zoom, but I'm glad that we have these technologies that mean I can sit at the other side of the globe and reach out and talk to you about what I find to be a very exciting time in cosmology, a time in which we have developed a standard model, a time in which we have seen these deep mysteries of dark matter and dark energy that lie ahead as challenges, and a time at which we can be applying these exciting new techniques from fields like machine learning to learn more about the basic properties of the universe. So let me stop here and take any questions that you have on the talk. Thank you.
Спасибо большое, уважаемый профессор. Очень интересная лекция.
Thank you, Professor. Your lecture was quite contentful, interesting, and it actually we are really impressed with the scale of the work that was carried out by you and by your colleagues. And we never even give a thought that this kind of work would have been possible to do. I can see that no questions from audience yet, but I have one question, and we are seeing all the time simulations in respect of our universe, and at the time of the Big Bang, it is depicted as a big balloon, as a big sphere. And at the beginning, it was at the beginning of your lecture, that the shape and the age was measured. And then my question is that what is the shape of our universe? That's my question.
The shape of the universe turns out to be remarkably simple. The geometry that we learned early in school, the geometry of Euclid, the sum of the angles of a triangle is 180 degrees. The idea that that's geometry of flat space is valid not only on that test you took as a 12-year-old, but it's valid on the scale of the universe. And that's quite an exciting thing to realize, because that tells us about the universe's fate. In general relativity in some ways can be reduced to a very simple idea. Matter tells space how to curve, and the curvature of space tells matter and light how to move. So if the density of matter was very high, space would be positively curved, and the sum of the angles in a triangle would be greater than 180 degrees, much like drawing triangles on the surface of a sphere. I can go all the way around the North Pole on a straight line. On flat space, I can't do that. I go off in the direction. If the density of the universe was very low, space would be negatively curved, shaped like a hyperboloid or a saddle. The sum of the angles of a triangle is less than 180 degrees. So the geometry we're seeing suggests the universe has just the right density to be on the balance between being positively curved and negatively curved. Space is flat. And the universe's geometry is linked to its destiny. If the universe's density was high enough that gravity was strong enough to make it positively curved, the expansion of space would eventually stop. The universe would turn around and collapse in a big crunch. The universe would end in tens of billions of years from now, nothing we need to worry about immediately, but it would be our fate that it would end in a big hot crunch, reversing the Big Bang. What we're seeing is a universe that will expand forever, get colder and colder, emptier and emptier, and our future fate is not a hot death, but a cold one. And that's directly tied to our geometry and the geometry of being flat and being filled with dark energy.
Спасибо большое. Еще один
Thank you.
вопрос
One more question
по поводу возраста Вселенной.
concerning the age of the universe. Any figures that we have identified by now?
Yeah, our best estimate of the age is about 13.77 billion years. And that's an interesting number to think about because the age of the Earth is about 4.5 billion years. So it's, the universe is about 3 times as old as the Earth, which shows there have been previous solar systems a chance to build up the abundance of carbon and iron and some of the components that make up our solar system by multiple generations of star formation, but not that many. In some ways, our universe is relatively young. All these questions of when you say the universe is 13.8 billion years old, an immediate question that some of you may have is, what was there before? And our best answer is, we don't know. We don't know if time started with the Big Bang, and asking what was before the Big Bang is asking like what is north of the North Pole. That is the answer that Stephen Hawking would have given. Pardon? Or as some people would argue, the universe has gone through multiple stages of collapse, re-expansion, or that another possibility is that it emerged from some quantum fountain. At the moment, we lack the theoretical tools we need to address this question. To answer this question, we need to be able to combine our ideas from general relativity, one of the great ideas of 20th century physics, and quantum mechanics, another great idea of 20th century physics, in a consistent way that we can extrapolate back through the Big Bang and figure out how it all started. We don't know how to do that yet. More work for some of the young people listening to do.
Понятно. Спасибо большое. И еще один
That's
вопрос.
clear. Thank you.
Вещество, о котором вы говорили.
And also about dark matter, I have another question.
Вещество, оно
The dark matter,
взрыва, либо оно и сейчас присутствует в нашей Вселенной.
was it existent yet at the time of the Big Bang, or it just got, engendered later?
So we think that soon after the Big Bang, the universe was a hot plasma of electrons, positrons, photons, quarks, antiquarks, and that the dark matter depends actually on what the dark matter is. We believe that the dark matter was produced in the first second of the Big Bang, but whether it was produced, it was there in the first, say, nanosecond, billionth of a second, or was produced during that first second, depends on what the dark matter is. We have many different ideas for what the dark matter is, and different models would give different answers to your question. So right now, there are many experiments worldwide looking for different dark matter candidates, many theoretical papers speculating on what it might be, and we will, different questions would give different answers to that, of when it was produced. It was produced early. It was certainly there at the time, 300,000 years after the Big Bang when we're looking at the microwave background, but we don't know how early that was. We don't have observations that directly probe at before that time.
Спасибо большое, уважаемый профессор. Как вы отметили,
Thank you, distinguished professor. As we all know, it is not possible yet these days to meet each other physically, face to face. But anyway, I would like to invite you to our hours of university in order to meet our students and to meet our researchers, and perhaps we could devise joint projects for ourselves and start those kind of joint projects.
Well, I look forward to the opportunity to be able to travel more and to visit. That would be a pleasure. I encourage you and any faculty or students who are interested in working with some of these numerical simulations. We've made our data available in ways to encourage people really throughout the world to have access to it. And I'm a big believer in the importance of the openness of science and the interactions of the scientific community throughout the world. So thank you for your attention and for the invitation to speak with you.
спасибо большое, уважаемый профессор.
Thank you, Professor, and we wish you success in your work, good health, and we wish you to have even more discoveries for us so that we could know more about our universe.
Thank you.
До свидания.